breaking onto an encryption is really also not happening these days, right? But it will for sure come back, right? So I mentioned NIS2, this law has been blocked, in particular apparently the DGSI, so the police intelligence, is against the fact that it would be illegal to put backdoors in messaging. There have been Florent Boudier, who's a member of parliament, has been nominated by the Prime Minister to find a solution to this problem. It was in January, and he was given 3 months. So I don't know if the report is public or not yet. I don't know if it will be public. I wish it will be. I hope it will be. But anyway, I don't expect him to find a solution, right? 3 months was way too short. Interestingly, yesterday, there was actually this délégation parlementaire au renseignement who actually made this, so in English would be Parliament Intelligence Oversight Delegation, member of Parliament on Senate who are together talking about this, who basically say, yeah, we need to have targeted encryption, access to encryption communications, we should not weaken the security of systems, there should not be this anti-backdoor law because it's going to be a real problem. And yes, intelligence needs to access the data anyway. So yes, although they say somewhere we need to do this with be very transparent, provide all clear debate and so on. Questions? What should we do from here? Do we ensure new access mechanisms do not weaken system security? I don't know how to do this. What are the guarantees we can provide? Shall we exclude police, government, military? Probably not. I don't know. How do you handle jurisdiction? Even if you implement it technically, jurisdiction is, for me, impossible to solve, right? The question is, these questions they are partly technological, sociological, political, legal. It's a society question, right? So not one, I'm more like technological level. I'm not going to solve the problem by myself, right? My question is, what do you do? Right? It's your turn. So, what are your solutions to this? Right? Okay. Thank you.
Thank you, Aurélien. Questions for Aurélien? Who wants to debate? Yep. Marc.
Thank you, Aurélien. Very interesting talk. So, my question is the following. So, you made it very clear that people are arguing about a solution, a backdoor or other decryption of in-transit data, so solutions, whether or not they should be used. But shouldn't we actually start by describing properly what the problem is that we try to solve, and then maybe there are, for the different problems, there would be different solutions that would be acceptable and possible?
Yeah, absolutely. That was a kind of the idea of talking about the data at rest, the data in transit, and so on, right? The thing is, there is definitely not one solution for every problem. The thing is that, in general, if you read this report from this commission of the parliament, they say, like, okay, intelligence agencies want to access the data, right? And they need to be able to access the data. And we need to, right? My position is also, okay, but there is already a lot of data available, right? Do you also need the content, right? You have the metadata, you have all the tracking, all the advertisement data, etc. So there is, if you compare from 50 years ago, even though we don't have a phone wiretap, the intelligence agencies, they have huge amount of data, right? And the question is really, are they really exploiting this data already good enough, right? And then, to which degree we can access to which different system, like live communications or stored data or accessing a phone that has been seized and so on. And these are different problems, definitely.
Question. Don't be shy. Well, I guess I have one for you. So it rang a bell when you discussed cost proposal. this is not typical. This is not especially related to what's discussed today, but it rang a bell regarding Adobe law, when they used to spell government peers sharing the data with you so that they could grab your IP and then shoot the letter. You know, so I guess the question is. Do you know if this has been decided by law and if they went rogue regarding that, or because it's like it's super technical, and I mean, yeah. So
you mean for Adobe? How was it done?
When you would go to Pirate Bay or anything like that, a public tracker, you would download something and they would grab your IP by peering with you. You know.
I think this is already in place. So
but the question is, so because it looks like some government doing rogue stuff. I mean, legal in some country, but maybe not in other country. But you know, you can't control which peer is going to peer with you, right? So, you know, I am always amazed that we are authorized to do so on public trackers without being, you know, annoyed by other countries like US, for instance.
But I think that's really the problem of jurisdiction, right? Each country makes its own laws, and that's part of sovereignty as well that we mentioned. If you're a country and you're sovereign, you can make your own laws. Actually, the sovereignty is limited. If you look at an Arendt, for example, who's having a very negative view of sovereignty, sovereignty is going against all international treaties on human rights and so on. You are a state, you do whatever you want, right? That's the bad side of sovereignty. And that's exactly this, right? Do you make your own laws on how these work internationally? So this is why actually there is a lot of debate about this at the European level, because you need some coordination. But it needs to be broader, and the problem is that you will never have everyone to agree about everything. And definitely, yes, if there is a judge that somewhere that says something, it's legal in this country. It's hard to go against, right? So definitely jurisdiction is a huge problem, especially for legal access, right? If you want, that's always, if you compare to the old world, it was not a problem because you had telecommunications going over cables, going over some telecom operators. The telecom operators had like a physical box somewhere. You could access the box and access the data there, right? Today, there is nothing in this box. And, okay, I mean, if you're using Signal, you have some server here and there, but they are not really important. You can replace them, and you could have distributed systems. You use Matrix, you have completely distributed systems. And, I mean, you cannot tell Matrix, now give me access to, right? Or you will be detected. And if you are detected, then it's counterproductive. So, yeah, I don't think there's a very easy solution to this. And I think this push is counterproductive, right? In trying to backdoor all messaging. Okay, yeah, maybe they can force WhatsApp on to do something, but maybe WhatsApp will lose a lot of customers as well. And people, or especially the criminals, will not use WhatsApp anymore. So,
thank you.
Okay.
Yeah, we have to go to the next. I have a few questions for you offline.
Of course, feel free. I'm here today, tomorrow, so feel free to come to chat. Thank you very much.
Aurélien. Thank you so much. All right. The next talk is a long presentation by Nathan Maillet, who is a PhD student at LAS CNRS, the former lab I mentioned during the introduction. The presentation is titled Brace Yourselves, Key Recovery from Side Channel Power Analysis Attacks on Non-SIMD HQC Decryption. So if you didn't get it, as I didn't, initially, this is about, a breaking HQC implementation that would be production ready using side channel attacks. If you're ready, you can. The floor is yours.
Hello. All right, so let's speak about some side channels, shall we? I will present to you a joint work with Cyrus Nugier, Vincent Miglior, and Jean-Christophe Deneville. And just to remind you of some keywords, let's speak first of side channels. So when you are doing some computation, you can view it as a black box, or you can think of it as a physical process being done by your CPU. And during the computation, if you have anything like timing or the electromagnetic field, which depends of the secret well, if you measure it, you have some dependence of the secret, and you can retrieve some information from it. And it's the same from the power consumption and variation of the power consumption. And so I will talk about key recovery from side channel power analysis attacks on non-SIMD HQC decryption. So SIMD stands for single instruction multiple data, which is some kind of parallelism. And HQC is a key encapsulation mechanism based on asymmetric crypto. All right, so for the power consumption, well, when you measure the variation of the power consumption, you can have some models based on the general purpose registers, and it's leaking some information, and some attacks have been made which uses such information. For instance, we have Platypus, which uses the Intel RAPL monitoring, which is some kind of monitor in your CPU in order to send to the kernel some information about the power consumption of the CPU. And Platypus is an attack taking advantage of it. So it breaks the kernel ASLR. It can leak some iOS keys using Intel NI, which is some extension of the instruction set for cryptographic instructions. And it leads to two CVEs, both of them having a CVSS of 5.5. So it's quite important. And we have another one, for instance, Earthbleed, which is a power to timing side channel. It's using DVFS, so dynamic voltage and frequency scaling. The idea behind this is that, well, when your CPU doesn't have much to do, it will reduce or modulate the frequency. And doing so implies that you have some model in the CPU for what's important for him or what will cost him a lot. And so it means some power models, but it will translate into timing models as the frequency will change. And thanks to, well, or due to Earthbleed, we can break a lot of crypto, and we can counter some protections for pixel stealing attacks. We have 3 CVEs following the Earthbleed attack, the 3 of them having a CVSS of 6.5. All right, so now let's dive a bit in HQC. So as I said, HQC is a key exchange mechanism, and in fact it's based on code-based encryption. So the code correcting codes which are used in HQC is the same principle as the one used in telecommunications. So first of all, you have a message to send, and you will encode it. So you have the encoding messages represented by M times a matrix G. And the idea is that you have some redundancy. Okay, you have some redundancy, and if you have some error in some bits of your redundant message, so the code word, you will still be able to decode it to the message being sent. So you have some neighborhood around which if you add some error, you can still come back to the message. That's the basic of it, and the idea of HQC is that you use the public key to encode it to some value named V. And it's too far. It's not in the neighborhood of your message. So someone having this V cannot decode it to the message being sent at first. And if you have the secret key, well, in fact, you can recover it by coming back in the neighborhood with higher probability. And then decode it using the code correcting code. So if you view HQC as a scheme, you can have Alice and Bob, and Bob wants to send a message to Alice. And to do so, Alice sends him a public key. Alice has some secret key, which is composed of X and Y. Oh. Okay. And Bob will encode its message, which is MG, and will add some error to compute the V, and it will send also a certain U. And when Alice receives it, she computes V minus UI, which is the the part where you comes back in the neighborhood of your code word, and she decodes it. And what we showed is that if you have the v-ui, which is being leaked, I will see it later, which is being leaked at the beginning of the decoding part, in fact, you can recover the secret key, so X and Y. All of them, all of the low case letters here can be viewed either as vectors, binary vectors, or as polynomials. So what we do on HQC, or what can we do on it? Well, we have done multiple things. First, we showed two side-channel attacks on the SAMD-less implementation of HQC. So HQC was being was a proposal at the NIST competition, and it won it. And as such, it has two implementations, or at least two major implementations. A reference one, which is not being meant to be used in production, and then an optimized one, which is being meant to be used in production, and which is tempered against some types of side channels, mainly timing side channels. So we showed two side channels on it. First one, a theoretical one at the ISA level, so at the architecture level. And we also have done it on real hardware, but we saw that, well, we have another leakage stemming from the microarchitecture, and so we have another attack. And we also proposed some countermeasures to this. So for the SAMD part, why did we remove the SAMD, or is it still useful? Like, does the attack still mean something if we remove the SAMD? Well, in fact, if you remove it, you have a portable IoT-friendly version as well. If you don't have a SAMD module, well, you don't have a choice, so it's quite important. And in fact, on the particular function we attacked, if you take it alone, it's even faster without the SAMD part. So it's quite interesting. This work is not the only attack on HQC, and it follows a lot of attacks on it since it's being a candidate in the NIST process. And it's the first one, to our knowledge, only recurring one oracle call. So you have some side channel with perfect accuracy, which gives you what's best. And you only have to run HQC once to get it. And it's a power side channel attack. You had some electromagnetic attack and timing attacks also. What's interesting to see is that you have a lot of reference implementations that are being attacked. So people are attacking versions that are not meant to be secured, neither used in production. So quite easy to attack, I guess. And for the architecture level, well, as we have multiple architectures, in fact, we needed two versions. So we have a variant for this one, specially made for the x86-64 architectures. And both variants works on a lot of architectures with nearly all optimization flags. So it's quite portable for an attack. And for the real case attack, we only need some traces. Like, it's not a lot. It's because we have some noise. I will come back to it later. And for the countermeasures, we propose 3 of them. I will also come back on it later. But what's interesting to note is that we can use them to mitigate other attacks. So here's a HQC encoding. So as I said, it's based on concorrecting codes. So you have a message and you encode it. In fact, in HQC, you have to use multiple codes to it. So you do one, and then you take it as the message entry for the next one. And the decoding is the other way around. And what we leak is the v-ui part. So first of all, let's assume that this v-ui is being leaked by side channel. Okay. So we know this v-ui part. And let's also assume that U is invertible. It's not always the case, but to begin with, we will start with U being invertible. it's easy to show that, in fact, we can recover y from this, and then we have x, so we have the secret key being used by Alice. Now we showed two theorems on U. The first one is a security reduction on U. In fact, with the specific mathematics structure used in HQC, we can view multiplication between two vectors as a multiplication between a vector and a matrix, which is the circulant matrix of U. And if you take some U, you can brute force in n, which is being the length of the vectors minus the rank of the said matrix. This value is the number of bits you have to brute force in order to recover Y. So if the rank of the said matrix is low, it's quite not interesting, but if it's high, it's quite interesting. So we showed another theorem, which is that the rank of the said matrix can only take 4 values, 0 and 1 being cases of failure of HQC, so it nearly never happens. Its probability is really, really low. And you have two other values, n-1 and n, so in the n case, it's invertible and it's easy to recover. And in the n-1 case, which is happening half of the time, the other half being n, what we showed thanks to the first theorem is that you only have 1 bit to brute force. So I think that most of you can do it. All right, so now that we showed how to recover the secret key thanks to V minus UI, let's see how we can get this value. So here is the C implementation of HQC of the optimized one. And it's the beginning of the decoding part of HQC. So what we see here is that we take this value of V minus UI, which is in the SRC part, and we take it bit by bit. So it's quite interesting. It's not giving all the side channel, as it's only C code, but we see that it could be interesting, and we could recover bits, each of them one by one, so quite easy. So what we have done is that we have looked at the assembly code being outputted by the compiler, which is seemingly like more or less this in the loop. So you have two registers, T0 and T1. And if you look at the values of the register T1 during the execution of the loop, what you have is that you can extract the bits B15 when E equals 14, B15 being a bit of the secret, so it's V minus UI. And what's being linked by side channel is the Hamming distance between the two values of the register T1 before and after the right shift. And here the Hamming distance is in fact, well, only B15. So this leakage gives us directly 1 bit. And if you look at the previous execution in the loop, what you have is that knowing the other bits, you can recover the bit being computed. So doing so, you can recover part by part and bit by bit each bits of the minus UI value. So here we have some attack working at least on the architecture level, and we have to see if it's still working at the microarchitectural level, and if it's not being like thrown out due to some weird stuff being done by Benoit, for instance. So when we have reproduced the attack on Cortex M4, what we had is this graph. So what you have in the X, the abscissa is the variation of the power consumption, and we have made a graph. Like we have done the computation for bits, and this bit can either take the value 0, which is being the one in blue, and or it can either be 1, which is the part in red. So what we see here is that we don't even need to know what are the other bits value, as we have seen in the architectural attack. we only have to like the only thing leaking, it's even easier because it's the bit being computed. So what you have is the leakage of the V minus UI part, but you have some noise, obviously, because the Cortex M4 is not perfect, and the probe is not perfect either. So if you have some noise, and if you have this, well, you can just continue with the attack, and if you do multiple measurements, you will reduce the noise you have on your measurements, and you can recover with more probability the V minus UI with a higher number of traces. So you just replay the attack, and with 80 traces, you have like for sure this V minus UI part, and so the secret key. The category being marked here are the security levels being defined in the NIST competition. So the category 5 being the most secure, but against the side channel, what can they do? And the first one being the less secure. This graph could be improved either with algebraic attack or with better hardware, better probes and such. All right, so we also have proposed 3 countermeasures. The first one being that, well, the decoding part or at least the beginning of the decoding, which is a decoding of a duplicated Riemann-Muller code, is leaking. So what can we do to as a countermeasure? Well, we can change the decoding part. So if we don't have this exponent sum function that's leaking, well, we don't have the same attack, which is possible. You just have to remove the code, but you still have to protect this other decoding. So here is a minimum distance decoding, and it's easier to protect against side channels using some stuff like masking, but the output is still difficult to get as a masked value. But at least our attack doesn't work anymore. You can also add some noise. So when Alice receives the message from Bob, when she computes the V minus UI, she samples some random error, and she adds it to the V minus UI part. So when the attacker gets V minus UI, he gets V minus UI plus the error, which he doesn't know. And so you cannot reproduce the attack with only one oracle call. You have to sample at least two values. So you need at least 2 oracle calls. It's not a perfect attack, but it's still a countermeasure. And you have to make the error. Well, the error should be should have a high Hamming weight. If you add too much errors on it, well, you have more decoding failure rates. So you increase the chances of your KM not working. So it's quite something to find in order to still have something secure but working. And you can also, in the same idea, do some code 1 masking. So when receiving the U and V values, what you do is that you sample some random message, you encode it, and you add it to the V minus UI part. And thanks to the code being used in HQC, the decoding of V minus UI plus this message will give you the message plus this sampled second message. So you can remove it after after decoding, and as with the noise part, it also requires an attacker to do at least 2 oracle calls. So it's another countermeasure, and you can do multiple countermeasures. It could be interesting, but they still have some bad points, and they have some overhead to it. For for the minimum distance decoding, it's the easier one, and we only have done those measurements about the overhead with the reference implementation, as it was easier, but it's only to get an idea of which one is the easiest and what's the overhead as a gross part. And the minimum distance decoding is like 5% more